You've sourced sand for your concrete mix. It looks clean, but what if it's full of invisible silt that will weaken your structure? Or what if its particle size is wrong, making your concrete harsh and unworkable? Fine aggregate makes up about 25 to 35% of the volume of your concrete, and its properties are just as critical as the cement and coarse aggregate. Ignoring sand quality is a direct path to high water demand, poor strength, and surface defects. In this video, we're going to uncover the essential quality control test for fine aggregate. I'll walk you through the key tests that will tell you everything you need to know about your sand, from its particle distribution to its cleanliness, ensuring you use only the highest quality material in your mix. Let's start with the most fundamental test, the one that defines the very character of your sand, the sieve analysis or gradation test. This test determines the particle size distribution of your fine aggregate. Why is this so important? A well-graded sand, with a continuous range of particle sizes from the largest down to the finest, has less void space. Less void space means you need less cement paste to coat the particles and fill the gaps, leading to a more economical and often stronger mix. It also drastically improves the workability and cohesiveness of fresh concrete, reducing the risk of segregation and bleeding. The procedure involves taking a representative sample of dry sand and passing it through a nested set of sieves, starting from a 4.75mm sieve down to a 150-micron sieve. The sieves are shaken mechanically for a standard period. The material retained on each sieve is weighed, and we calculate the cumulative percentage passing. This data is plotted on a gradation chart, and the sand is classified into one of four grading zones: Zone 1, 2, 3, or 4 as per IS 383 or ASTM C33. Zone I is coarse, Zone 4 is fine. A pro tip from concrete technologists: Zone 2 sand is often considered ideal for most general concrete works, providing a good balance of workability and strength. Sand that is too fine, Zone 4, will require more water and cement, while sand that is too coarse, Zone I, can produce a harsh, unworkable mix. Now let's talk about cleanliness. The presence of excessive silt, clay, or dust in your sand is a concrete killer. This is why the silt content test is a non-negotiable, quick field check. These fine particles are smaller than 75 microns and are harmful because they form a coating around the sand grains, preventing a proper bond with the cement paste. They also increase the surface area of the aggregate, demanding more water to achieve the same workability, which weakens the concrete. The test is simple but powerful. We take a 50-gram sample of sand and place it in a 250 milliliters measuring cylinder. We add water until the level reaches 100 milliliters, then another 50 milliliters of a 1% salt solution to help the silt settle. We shake the cylinder vigorously and then let it sit for 3 hours. The silt and clay particles will settle on top of the sand layer. We measure the height of the silt layer and the sand layer. The silt content is the height of the silt layer divided by the height of the sand layer, multiplied by 100. As per IS codes, the silt content should not exceed 3% for crushed sand and 5% for natural sand for reinforced concrete work. If it exceeds this limit, the sand must be washed before use. This is one of the most common causes of low concrete strength on site, and it's so easy to check. The next two tests are often conducted together and are critical for precise mix design: specific gravity and water absorption. Specific gravity is the ratio of the weight of the aggregate to the weight of an equal volume of water. It indicates the density and solidity of the sand particles. A higher specific gravity, often around 2.6 to 2.7 for good quality sand, indicates a strong, non-porous material. Water absorption measures the amount of water the aggregate can absorb into its pores. This is crucial for mix design because if the sand is highly absorptive, it will steal water from the mix, reducing workability and affecting the vital water-cement ratio. We determine these using a pycnometer. We find the weight of the pycnometer filled with water, the weight of the pycnometer with a sample of saturated surface dry SSD sand, and the weight of the oven dry sand. Using these three weights, we can calculate both the specific gravity, SSD, apparent and bulk, and the water absorption percentage. For a quality mix, you want a consistently high specific gravity and a low water absorption value. A high absorption value means you must account for this water in your batching calculations to avoid a mix that is too dry and unworkable. Another critical test, especially when using natural sands, is the organic impurities test. This test detects the presence of decayed vegetation, humus, or other organic matter which can interfere with the hydration of cement, severely retarding the setting time and reducing early strength. The test is a simple colorimetric analysis. We fill a 12-ounce glass bottle with a sample of sand up to the 130 milliliters mark. We then add a 3% solution of sodium hydroxide, NaOH, until the volume reaches 200 milliliters. We shake the bottle vigorously and let it stand for 24 hours. After 24 hours, we observe the color of the supernatant liquid, the clear liquid above the sand. If the liquid is colorless or has a light straw yellow color, the sand is acceptable. If the color is a deep brown or dark, it indicates a significant presence of organic impurities, and the sand should be rejected or washed thoroughly. This test prevents one of the most baffling field problems: concrete that just won't set. Finally, let's discuss a highly practical on-site phenomenon: bulking of sand. Bulking is the increase in the volume of sand due to the presence of moisture. When sand is damp, a thin film of water forms around each particle, pushing them apart due to surface tension. This means that a given volume of damp sand contains less solid material than the same volume of dry sand. If you don't account for this, you will end up with a sand-deficient, overly harsh concrete mix. The extent of bulking can be as high as 30% at a moisture content of around 5 to 8%. The test is straightforward. We take a sample of damp sand and fill a container, noting its height. We then add water, submerging the sand completely. The surface tension is broken, and the sand volume settles to its actual volume. The difference between the initial damp height and the final saturated height allows you to calculate the percentage of bulking. A pro tip for site engineers: always batch concrete by weight, not by volume. If you must batch by volume, use a bulking chart or the simple test to correct your measurements, ensuring you get the correct proportion of sand in every batch. In conclusion, testing fine aggregate is not a luxury. It is a fundamental requirement for quality-conscious construction. Each test tells a vital part of the story. The sieve analysis ensures workability and economy. The silt content test guarantees bond strength. The specific gravity and absorption tests feed into your precise mix design. The organic impurities test prevents setting failures, and understanding bulking prevents on-site proportioning errors. By rigorously testing your sand, you transform it from a cheap, generic material into a high-performance, engineered component of your concrete. This disciplined approach is what separates a professional, durable project from a problematic one. Now I want to hear from you. Which test for fine aggregate have you found to be the most revealing on your projects? Was it the silt content test that explained a strength issue, or the bulking of sand that solved the workability problem? Let me know in the comments below. If this guide to sand testing has been valuable, please give this video a like and subscribe for more content that helps you build with confidence.